Hi, this is Zhuotong Li, and another group member is Yan Zhu. We studied the topic one computer vision. So, in the realm of disaster management, effective identification of disaster types through images, particularly satellite image, plays a crucial role in enabling timely reporting and accurate assessment for rescue teams to devise appropriate response strategies. Deep learning models, especially convolutional neural network, also called CNNs, are widely used to classify disaster images. While powerful, this model often functions as black boxes, recognizing image features without manual input. There are some studies related to our topics. For example, a study using BGG and EULO algorithms analyzed disaster-related images from social media to identify disaster types with 96% classification accuracy through EULO. However, it relies on cloud-based algorithms and a limited training dataset of 1,500 images, made it less applicable for real-time crisis management. But our research advanced beyond previous work by employing logistic regression model to understand feature importance and analyze image classification coefficients, and also consider more than one kind of disaster types. So let me introduce what our data looks like. In this study, we utilize the XView2 challenge dataset comprising 26,000 images to analyze disaster types and their characteristics. The data includes disaster images from Hurricane Matthew, SoCal fire, and Midwest flooding. Each image is categorized by attributes like damage level, dimensions, and color profile. On a damage scale from 0 to 3, which is also shown in the picture, the overall average damage level is 0.654, with Hurricane Matthew including the most severe damage, following by SoCal fire and the Midwest flooding with lighter impacts. Specifically, 15% of Hurricane Matthew images shows level 3 damage, compared to 12% of SoCal fire and just 0.84% for Midwest flooding. When analyzed by disaster type, hurricane images shows high blue intensity due to significant water presence and have a wider format to capture their sprawling nature. Fire images are predominantly red, highlighting the fiery environment with more square dimensions reflecting localized impacts. Flood images are categorized by a balanced mix of green and blue, aligning with the unpredictable spread of water. Regarding damage levels, images categorized as level 0, which means no damage, exhibit balanced colors and average dimensions typical of undisturbed landscapes. Images with level 1 minor damage displaying slightly increased in red and blue, encompassing broader regions with scattered disaster. Level 2, which is moderate damage, images in this category reveal marked changes, particularly in red spectrum, with wider dimensions capturing broader disaster impacts. Level 3 is severe damage. The images in this category shows the highest color deviations, with notable increase in red, reflecting widespread devastation and requiring the largest dimensions to capture the extent of the damage.
Because we faced tests to project the levels and the types of different disasters, so we choose a logistic regression. First, we split the data into training as the test sets with a test size of 20%. Then we adopt a random selection to ensure all features use the same data. We set the random state equal to 42. And then we conduct feature engineering by comparing the performance of about 10 features. We select 6 features finally. And to ensure that features contribute equally to the distance of computation, we standardize all the features. This approach also helps us to speed up the convergence of the algorithm. And then we begin to train and test the data. The highlights of our methodology is the usage of different features. We used 6 features finally, and they are classified into 3 types. The first one is texture-related features, including local binary patterns, gray level co-occurrence metrics, and edge features. It's interesting that we find all these features will use the gray filters first. And the second type is the color features, including color histogram features and average color features. Finally, we also include the histogram of oriented gradient features, which focus on edge directions, strengths, and shapes, kind of like a combination of the color and the edge characters.
So based on the methodology and data graph, the original data was divided into training and validation datasets. Our combined feature model, which includes 117 features per record, demonstrated an impressive accuracy of 0.99 in predicting disaster types between fire and flooding, and the F1 score for predicting hurricane levels stood at 0.71. We employed the PCA to assess potential overfitting, reducing the feature set to 33 principal components. This adjustment slightly increased our disaster type prediction accuracy to 0.99285, indicating that some discarded components were likely noise. However, the F1 score remained unchanged. Additionally, using L1, a regulation with a linear solver, slightly reduced accuracy in predicting disaster types to 0.98, with an F1 score of 0.714, suggesting better generalization over the initial full feature set. Further, we want to check if our model works well on all kind of disasters. We analyzed those 3 disaster types and choose the result as a following table. Without PCA, the model achieved an accuracy of 0.967 for type prediction and F1 score of 0.66867 for level prediction. However, post PCA accuracy dropped to 0.92 with an F1 score of 0.66, possibly due to the loss of crucial information with lower variance components or amplification of noise. F1 regularization resulted in a slightly lower accuracy and F1 scores compared to the full feature set. In terms of feature performance, we found that the local binary pattern, also called LBP feature, proved the most effective, particularly for disaster level and type predictions, highlighting the importance of texture over color in disaster imagery analysis. Color features showed significant variation in effectiveness. Color histogram features provided detailed information about color distribution and variance, proving more useful than average color features, which only offered a general view of color composition. Texture-related features, including combined textural and edge features, demonstrated their value, with LBP leading the predicting disaster types, underscoring the crucial role of texture in differentiating disaster impact areas. This comprehensive analysis underscores the complexity of predicting disaster types and levels using machine learning models and highlights the impact of selecting appropriate features and regularization methods to enhance model performance and generalization in disaster image analysis.
Although our model is at a very high F1 score and the accuracy level, there are still some limitations. First is the possibility of multicollinearity. We use different features, but sometimes for different features, we will process them using the same color scale. So the duplication of information may lead to multicollinearity. Second is the trade-off between the computational power and the complexity of models. When new features are added, generally our model has a better performance, but the computer works very slowly. As for future research, 3 kinds of data will be helpful in similar topics. First is the latitude and the longitude data, and the second is time series data. This data can help us to project the location and the disaster types. Third data is data for other disasters, which can help us to generalize our conclusion. As for the social impact, our model has a very high accuracy level, helps to overcome the shortcomings of some traditional models like convolutional neural network. And models for similar research are also very useful for projecting future disaster events and to evaluate economic loss. Finally, is the ethic issues. We find that when some agencies take pictures of disaster images, people's privacy may be unintentionally infringed. For example, the information of people's properties, their residential information. So there's a balance between the negative social impacts and the positive impacts of these models and the research. So the next step is for the government to regulating the usage of this data. And thank you.